Okay, now we're going to see the Newton's method. It's very similar to the secant method, but instead of finding the secant line and then finding the zero of the secant line being our next iteration, we just find the tangent line. This time we're going to need to use the derivative of the function. So the idea is this, so let me draw the picture for you. Okay, here's a general function, f of x, and again we're interested in finding the zero of that function. So we're going to start with an initial guess. Let's say, for example, my initial guess is here, okay? That would be my x naught, or x1, whatever you want to call it. So that x1 will give me a y value of y naught. And now we're going to use the tangent line. Now we are assuming that this function here is differentiable, so you can find the derivative at any point. So we're going to find the tangent line. So let's see if I can draw the tangent line here for you. Okay, here it is. And the tangent line will intersect, hopefully it will intersect the x-axis here. And we're going to find the zero of the tangent line. Okay. This is y. So we need to find this value here, which is the next iteration. Okay. So this would be your x1, your next iteration. And then once we find this next iteration, then find the y value of that, and then find again the tangent line again, and then intersect that with the x-axis, and that will be your third iteration. So it's an iterative process. So what we need to do here is to find the equation of the tangent line. Well, this is very easy. If you use the plane slope formula, y minus y1 equals to slope x minus x1. Well, the slope is just the derivative, right? The slope is the derivative of the tangent line, or the function which is the slope of the tangent line. So we can plug the point. The point is the initial point here, x naught, y naught. And the slope is the derivative at x naught. So it's a number we can find, x minus x naught. Okay, so that's the equation. So this is the equation of the tangent line. Y equals to y naught plus derivative of x naught, x minus x naught. Okay? This is the equation of the tangent line. Okay, now let's find the zero. To find the zero, we set the y equals to 0, then solve for x. So we set 0 equals to y naught plus f derivative x naught, x minus x naught, and then we solve for x. If you solve for x, then you will see that this is x minus x naught equals to, if I move the y naught to the other side and I divide by f derivative of x naught, then I get y naught divided by the derivative of x naught at x naught. And then move x naught to the other side, and that's the iteration for Newton's method. So x is x naught minus y naught over derivative of x naught. Okay, so this is the new iteration. Alright, and let's see how we code this. So let me go here to Notepad. Let me start a new function. I can actually use Mueller's function here and change it a little bit. Yeah, let's go ahead and do that. So I'm going to change here to Newton. And this time we need only one guess. Okay, we guess with x naught. The arrows start with the arrow being big. Define the tolerance. Here is my counting variable, so I can count the number of iterations. So we're going to have a loop while the error is too big, or is still big. Okay, well, the formula is here. Let me show you here down here. X equals to x naught. So all I need to do is to define x. x equals to x naught minus the y naught is f of x naught, right, divided by the derivative. Notice that we need to define the derivative. So we need to have a new function. So here's the function. Here's another file. That's the function that I'm working with. It's the standard, the old example, x squared minus 9, right? We're trying to find the zero of that function, which is the square root of 9. I'm going to actually create a function. Let's call it df.m, okay? Let's see, yeah, I need to create a new one. That's what I need to do. Function df, actually should be y equals to df of x, okay? And it's the derivative of this function here. So that's one problem in the Newton's method. I need to have not only the function, but also the derivative of the function. 2 times x. That's it. And save this. I'll save it as df.m. Okay. So here I have the derivative. Here's the function. Now I can call it from here. I can say df of x naught. Now let's compute the error. The error would be f of x. If you want, you could define this as x1. Okay, if you want x1. All right, this would be the new iteration, x1. Right, like I wrote here on the graph, right? New iteration. And then that's the error. I don't need this. But again, we need to transfer values, right? So remember that this is an iterative process. So again, let's throw out the boxes here. Here's x naught, and then here's x1, right? So if I start, for example, with a value of, I don't know, 4, and then for some reason I get the value of, I don't know, let's put something here, 1, okay? Again, I don't know if it's going to be 1. But if the error is still big, then the program will run one more iteration, and then I need to transfer this value here over to this box. So all I have to do is say x naught will take the value of x1. Okay, so we're transferring the values because, as you can see here, the new iteration uses the old iteration. So let's go back here. Let's put that in there. X naught equals to x1, and that's it. And the output here should be x1. So that's Newton's. Let me say that is Newton's. Newton.m. There it is. Okay, let's test. Put that in here. Here's octave. Let's see. We call Newton, and then an initial guess. Let's put, I don't know, 1. Okay, so it found the solution. The answer is 3, and it took 6 iterations. Let's try different values to see what happened. If I start with x, my initial guess being x equals to 4, then it takes 4 iterations. So that's Newton's method.